Okay, let's take a look at Newton's third law, and we're going to do an example where this is really quite critical. You might recall when we defined forces, we used the term due to and acting on. Now Newton's third law really wants to take advantage of that. So let's just think about weight for a second. If I'm talking about my weight, that's a gravitational force due to the Earth acting on me. So gravitational force due to the Earth acting on me. That would be the force due to gravity. Now Newton's third law states something like this. For every action there is an equal and opposite reaction. So what that means is if the Earth is pulling on me with some force, then I am pulling on the Earth with the same force but in the opposite direction. So if here I am, right here, and there's a gravitational force acting on me due to the Earth, here's the Earth, then what that means is that there must be another force acting up, and this would be a gravitational force as well, but this would be due to me, and this force is acting on the Earth. Now if I weigh 200 pounds, and I'm pulling on the Earth with a force of 200 pounds, the Earth really doesn't notice because its mass is huge. But that force still exists. So the action is a gravitational force due to the Earth acting on me. The reaction, all I need to do is take the due to and the acting on and switch them. So the reaction is a gravitational force due to me acting on the Earth. So notice this force is acting on me, this force is acting on the Earth. So if I'm looking at a force diagram for me, I'm concerned with this force. This equal and opposite force exists, but if I'm talking about a force diagram for me, I really don't care about it. So be careful about what you consider to be action-reaction pairs. Action-reaction pairs act on two different objects. So let's revisit the book sitting on the table. When I examined this, there was a gravitational force due to the Earth acting on the book, and a normal force due to the table acting on the book. And we came to find that the F normal minus mg were equal to 0 when I did the sum of the forces in the y direction. So F normal equals mg. Now, that tells me that these two forces are equal. One's acting up, the other one's acting down, so they're in the opposite direction. But it's important to note that that is not an action-reaction pair. Yes, they're in the opposite direction and they're equal in magnitude. But if somehow or another I pulled the table out from underneath, the book would still fall under the influence of gravity. And so the normal force in this scenario, where I pull the table out from underneath it, would disappear. So if the action is the normal force due to the table acting on the book, then the reaction is going to be a normal force due to the book acting on the table. And so those forces are equal and opposite, but they're acting on different objects. One is acting on the book, the other is acting on the table. So they're acting equal and opposite. So this is a really important thing to understand. So let's take a look at this diagram. What I have here is a truck, and what you're seeing here is the back of the truck. And on that truck are two beams. There's the blue beam and the yellow beam. And the blue beam is attached to the bed of the truck by virtue of this cable here. And the truck may or may not be moving forward. So let's just assume that it is. Let's give the truck an acceleration in the forward direction. So what I'm interested in is what are the forces acting on these beams. And what I'm going to do is I'm going to draw each beam separately and look at them separately. And we're going to assume that friction is in play here. So when I look at the top beam, the blue beam, I look at the forces acting on the blue beam, there's going to be a weight. So I'm going to call that m blue times g. And there's going to be a normal force. Now I'm going to label that as F sub O B. That's a normal force due to the orange beam acting on the blue beam. And then there's going to be a tension here, and that tension is due to the cable acting on the blue beam. And then there's also going to be friction. Now the frictional force is the interesting one, because what direction will the frictional force be? The way we answer that question is we assume there is no friction at all. Now if there's no friction, the tension in the rope is going to pull the beam to the right. But there's nothing to pull the orange beam. And so the orange beam is going to slide in this direction. Since the sliding is going to the back of the truck, the orange beam is sliding to the back of the truck, it must be rubbing the top beam towards the back. Look at it this way. If I am riding on the orange beam, I see the blue beam moving to the right, sliding to the right. Friction always opposes that sliding. And so the frictional force is going to be acting to the left. Now that's the frictional force due to the orange beam acting on the blue beam. And so there are the forces acting on the blue beam. So let me just write those out because it's really important. So this is a normal force due to the orange beam acting on the blue beam. This is a tension due to a cable acting on the blue beam. This is gravity due to the earth acting on the blue beam. And this is a frictional force due to the orange beam acting on the blue beam. And those are my forces. And I assume a standard x and y. Then my equations become some of the forces in the x. I get T minus F orange blue equals m blue, acceleration of blue. Not necessarily the same as the acceleration of orange. Some of the forces in the y, I get the normal force between orange and blue minus the mass of blue times g equals 0. There is no acceleration in the y direction. So we'll assume the acceleration is to the right, and this is the blue beam. If they're moving together, accelerating together, then the accelerations are the same. Now let's take a look at the orange beam. Now at least one force is easy, and that's the gravitational force, so that's m orange times g. The cable is not touching the orange beam, so there's no tension due to the cable because it's not touching it. The bed of the truck is touching it, and the bed of the truck is going to exert an upward force, which I'm going to call F truck acting on orange. So this is a normal force due to the truck acting on the orange beam. This is a gravitational force due to the earth acting on the orange beam. Now if there was no friction, as the truck moves forward, the orange beam would slide to the left, and because of that there must be a frictional force to the right. Now this is due to the bed of the truck, so I'm going to call that truck orange. So this force is a frictional force due to the truck acting on the orange beam. Now there are two other forces that we want to take into account, and we're going to get those forces from the previous force diagram. We're going to take advantage of Newton's third law. Notice I have a force right here, frictional force due to the orange beam acting on the blue beam. Newton's third law says there must be a frictional force due to the blue beam acting on the orange beam. And so, since I'm doing a force diagram for the orange beam, I need that force. Notice that force is to the left. So there's a frictional force to the right. I'm going to continue calling it OB because it's the same magnitude as the previous one, but in the opposite direction, which I've accounted for here with my arrow pointing to the right. So this is a frictional force due to the blue beam acting on the orange beam. I know I did not switch the subscripts, but I know what that is because of the previous one. In addition, notice this normal force right here. That normal force is due to the orange beam acting on the blue beam. And so Newton's third law says there must be a normal force due to the blue beam acting on the orange beam. Again, I'll hold my subscripts. Now in the previous slide, that normal force was up, so here it must be down. So FOB would be a normal force again. Same kind of force, equal and opposite forces are always the same type, due to the blue beam acting on the orange beam. And so you can see the force diagram for the bottom beam is really quite a bit more complicated. I'll assume the same x and y coordinate system, and the sum of the forces in the x, I'm going to get FTO plus FOB equals M orange times A orange. And it's highly likely that A orange is to the right and probably the same as A blue, but I won't specify that at this point. And then the sum of the forces in the y, I get F truck orange, that's positive, minus F orange blue, because that normal force is down, minus M orange G, and that's equal to 0. There is no acceleration in the y direction. Now notice if I solve this for F truck orange, that's the normal force due to the truck, it's equal to the weight of the orange beam plus, because those will both be positive when I move them to the right hand side, plus the normal force due to the blue beam. And so if there's a scale underneath the orange beam, that scale is going to read not just the weight of the orange beam, but also the weight of the blue beam. So imagine you weigh 200 pounds and a friend of yours weighs 110 pounds, and that friend of yours jumps on your shoulders. If the two of you stand on a scale, the scale is going to read 310 pounds. Now the scale only reads the normal force between you and the ground. But there's a force pushing on you that's equal to the weight of the person on your shoulders and the gravitational force. Those are going to add up to 310 pounds. And to counter that, the scale needs to give a normal force of 310 pounds.